Hello, my name is Tejas Savalya. This is a pre-recorded presentation for the 2020 meeting of the Society for Mathematical Psychology. I will talk about modeling the time course of visuomotor adaptation. Specifically, in the experiment conducted by Keger et al., participants make center-out reaching movements. Participants are asked to learn a 90-degree movement rotation mapping via two different learning mechanisms. In the sudden onset group, participants see the 90-degree rotation from the second block of the experiment, which lasts through the block 10. On the other hand, the gradual onset group participants encountered an increasing rotation by 10 degrees each such that the final learning block is 90 degrees rotated. After having trained participants again to the center out reaching movements without any mouse rotations. As expected, Kager et al. Found that after training, participants made erroneous movements in the opposite direction. However, even when the participants seem to have trained equally well to the rotation, in the final block without rotation, gradual onset group participants were much worse than the sudden onset group participants. Based on these findings, we hypothesize that sudden condition may induce model-based learning where participants plan their movements before they start moving. Gradual onset group may induce model-free learning, a more trial and error or procedural learning sort of mechanism. And we ask if we can test this manipulation. We can test this with a manipulation of speed versus accuracy emphasis. What we predict is that speed emphasis will make you more model free and make it harder for you to readapt in the transfer phase, whereas accuracy emphasis will make you more model based and make it easier for you to readapt in the transfer phase. In order to add this speed accuracy emphasis, in our experiment, participants were asked to focus on either being as fast or as accurate as possible in their movements. In order to facilitate this, at the end of each block, participants were shown a fake scoreboard indicating how well they did in a particular block. These are some trajectories that participants make in the sudden and gradual conditions. As expected, the participant in the sudden condition make more errors in the first learning block as compared to the participants in the gradual condition. In the final learning block, both participants make comparable errors, and in the transfer block, the errors are in the opposite direction. We quantify errors using angle differences. Specifically, an error of a trajectory is the mean of the angle difference between the actual movement direction and the ideal movement direction for each point on the actual trajectory. As was the case in Kager et al., we see more errors in the transfer phase of the gradual condition than in the sudden condition. We use state space models in order to quantify the trial-by-trial learning mechanisms. Specifically, the error on any given trial is the difference between the environmental rotation and the estimated rotation on that trial. This error is then used to update the rotation estimate via learning rate B and a retention factor A. We compare this single-state model to a more complex dual-state model. The dual-state model uses error feedback to learn two distinct fast and slow systems in a manner similar to the single-state system, subject to cross-system constraints on the learning rate and the retention parameters. The estimate of the environment is then the sum of the estimates of both of these fast and the slow system. Here, these are the fits on Gaussian smooth error data. While these fits look qualitatively similar, differences in the shape of these curves are more visible in the first few trials of the sudden group. These plots show parameter fits of the learning rate and the retention parameters for the single-state model and the two systems of the dual-state model. We use a future prediction error measure to compare these two models with different number of free parameters. This metric reveals that the dual-state model fits better to this data than the single-state model. Furthermore, we see significant main effects of rotation and emphasis on learning rate of the fast system, but there is no effect of rotation on the slow system. The model overestimates sudden learning as seen in the transfer phase fits. Fast system, we hypothesize, allows for quick update, which we think that this may correspond to model-based system, whereas the slow system, which allows for a higher retention, may correspond to the model-free system.